Okay, this is video is an introduction to the binomial distribution. Like the geometric, the binomial distribution is a type of Bernoulli trial. And remember, Bernoulli trial has a success failure. In other words, it's a yes, no situation. However, as we mentioned in the previous video or the video on when we talked about the geometric, just because it's a success failure doesn't mean there can't be more than one outcome. In other words, when I flip when I roll a dice, I can get a 1, 2, 3, 4, 5, or 6. But I might say that 5 and 6 represent my opportunity for success, and these would represent my opportunity for failure. If that were the case, I have satisfied the success failure criteria. Also, to be Bernoulli, the probability of success is constant. And we know that if I have 5 and 6 were to be what defined as success, the probability of success would be 1/3. The probability of failure would be 2/3, and it would remain constant because rolling a dice is constant. Further, the trials must be independent, and rolling the dice, one roll does not impact that of another roll. That said, there's one little caveat that's not going to be that important for right now. We will develop it much later. Actually, we'll develop it in the third quarter. But once again, if we have a very large population, like a giant pile of M&Ms, and I take an M&M and eat it, technically the percentages change. But they change so slightly, we don't worry about it, and we say they're independent even though they're not. So in other words, if our population is large enough and our sample is small enough, we don't worry too much about it. And basically, the sample needs to be less than 10% of the population, and it needs to be a large population. But once again, we'll talk about how large, et cetera, the population has to be next semester. That is not part of this, but I just wanted to give you a heads up that will be coming. So basically, we need 2 possible outcomes and success and failure. The probability of success needs to be constant, and the trials need to be independent. And for this quarter and for this section, this is what we will hold true to that. Now, the binomial is different than the geometric. Besides the fact that the formulas are different, it's a totally different distribution. And we'll talk about that in just a second. But first, probability of success, I use a P. I like to use Q as my probability of failure. However, if you use Q, you need to make sure that you define it as 1 minus P. So you may prefer to use 1 minus P. That's the way it shows actually on the formula chart. And we'll look at that in just a moment as to what it looks like. So first off, binomial distribution. What are its properties? Well, 2 possible outcomes, success or failure. The probability of success is constant, and the trials are independent. This is what it took to be the Bernoulli, all right? Now, that and a geometric both share the exact same at this point. Here's where it changes. In a binomial, we have a specified number of trials that will be completed, whether there's 1 successes or no successes or multiple successes. So binomial, whereas with the geometric, we continued until we had our first success. So technically we didn't have a specific number of trials. We might try it for 100 times or 1,000,000 times. We're just going to keep trying until we have our first success. With a binomial, we have a specific number of successes, and then a specific number of trials. So the binomial has a specific number of trials, and we're just going to do it for that number of trials. We're going to try it 5 times, 10 times, 20 times, and then we're going to go back and count how many successes we have. So geometric will continue until we have our first success. Binomial will have a set number of trials, and we're going to count the number of successes that we have. All right. And then it says number of trials, successes, and failures are discrete. In other words, they have to be counting numbers. And that's true for the geometric. All right. That is not true for the expected values. The expected values can be decimal answers, but the number of trials, the number of successes, and the number of failures are discrete. But you're going to have that the expected values can end up being fractional. All right, so this is the equation I use in my notes file, but that differs slightly from what they give you on the formula chart. So here's what they give you. They give you n choose x, the probability raised to the x power. This is failure, so this is what I use for q. So if I were writing this using their exact variables, I would chosen nq, choose x, p to the x, and then q to the n minus x. All right. Now, I want to talk to you about this. This is basically when we talked about combinations in one of the prior videos. We said that that was n factorial over x factorial, and this would be n minus x factorial. As far as showing that, you'll never have to show it. It's built into the calculator. We don't have to worry about it. Our expected value is just n times p. So the mu equals n times p, or the expected value. And then our standard deviation, I like to use NQ. However, they're going to use the P notation. So N times P, the probability of success, times 1 minus P, which is the probability of failure. And like I said, I tend to use NPQ just because it's shorter and easier for me to type in. However, either one of them will get you credit. But if you're going to use Q, make sure you say Q is 1 minus P. If you do that at the top of the problem, then you're good to go. All right. So a geometric is always phrased, or is typically phrased, what is the probability that the first success occurs on the fifth trial? That's different than a binomial, and it's typically phrased, what's the probability of a certain number of successes in a given number of trials? So what is the probability of having exactly 3 successes in 20 trials? So if I say, you know what, I have 20 trials, so I have 1, 2, 3, 4, 5, ... all the way to 20. And I say, what's the probability of having exactly 3 successes? And actually, I could have 0 successes. The probability of having exactly 3, I'm circling one number. So since I'm referring to a specific number, this is going to be a binomial PDF. All right, this will be a binomial PDF. And I can go to the calculator, and I can go to the second vars again. And I can go second vars. Should turn my calculator on. Second, followed by the vars. Oops. Second, followed by vars. And I can scroll down, and I have binomial PDF. And since in this case, I want binomial PDF is what I wanted. Right below it is a CDF. All right. So PDF is for a specific number of successes. Hey, I'm only accepting 3 successes. What's the probability of 3 successes? I don't care about 1, 2, 3, 4, 5, all the way up to 20. And my number of trials in this case would have been 20. Keeping the same number of trials, what is the probability of at least some number of successes given a number of trials? Well, since it's an at least, like we learned previously in probability, we're going to be working with a 1 minus. This will be set up as a 1 minus a CDF. And the reason it's a CDF is I say if 1, 2, 3, 4, 5, ... all the way to 20. If I wanted to have at least 4 successes, that means I'm interested in all of these values. All right, I'm interested in all of these values. Now, within an at least problem, I'm going to subtract out what I don't want. So it's going to be 1 minus binomial CDF and subtract out the highest value I don't want, which in this case is 3. So in this case, what I'd be subtracting out is the 3 and everything down below it, because I don't want to subtract out what I already have. And the reason we have a 1 in front, because if I add up all the PDFs, because a CDF is just a sum of the PDFs, if I add up the PDF of 0 plus the PDF of 1 plus the PDF of 2, all the way to the PDF of 20, I get 1 whole. All right. The next one, what's the probability of no more than some certain number of successes given a number of trials? Well, once again, if I had 0, 1, 2, 3, 4, ... all the way to 20, I said no more than 4. If I said no more than 4, that means I'm accepting 0, 1, 2, 3, and 4 as my answers. All right, anything above it is too big. So it's a binomial CDF of 4. Finally, what's the probability that the number of successes in a given trials are between two values. Have to be very careful. All right. So if I have 0, 1, 2, 3, 8, 9, 10, 11, 12, all the way to 20, and I wanted to know that it was between 8 and 12. So basically, has to be between 8 and 12. So what I'm looking for are the between values are 9 and 11. If that's the case, then it would be the binomial CDF of the highest one that I wanted, which is 11, minus the binomial CDF of the highest value that I didn't want, which happens to be 8. All right. So basically the binomial CDF of the highest value I wanted, and I wanted it between 8. I wanted it to be between 8 and 12. So I wanted it to include be 9, 10, and 11. So the highest value I wanted was 11. And then I subtract out the highest value that I didn't want, which is 8. All right. We will show examples of these problems in the next videos to follow. All right. Thank you for that.